Hi class, so this video is could be one of the most important uh, techniques that you will need to learn for theory of structures, so or for structural analysis, so this is another uh, displacement method, no called the moment distribution method, so kindly prepare yourself, and before you try to move on, you can try reviewing everything na my previous two videos involving the fixed end moments uh, and the slope deflection method, so somewhat they are related to what I'm about to teach you, so and another thing, if time will permit, this video, same as the slope deflection method, will contain three types of uh, videos, for or first for continuous beams, second for frames without side sway, and then frames with side sway. Pero I will try to focus more first on the continuous beams, So let's start, So moment distribution method, is a method developed by Hardy Cross, during the 1924, and was the widely used method for structural analysis during the pre-computer era, So it is a displacement method, in a sense na somewhat similar to the slope deflection method, but the only difference is dahil sa slope deflection method, we are directly solving, for the rotations, no using, we are directly solving for the rotation, for the slope, for the deflection, and we are somewhat trying to with again, I'll say, sa slope deflection method, we are directly solving for the rotations, uh, member by member, in order to uh, determine, the end moments that we need. Pero sa moment distribution method, we are gradually adding uh, all the load, that contributes, all the loads, and all the supports that somewhat contributes to the movement, ng structure natin, So ano yung mga load na nag nagko-cause ng deflection sa beam natin, and somewhat ano yung mga support na pumipigil sa kanya, and instead of the we solve it simultaneously, somewhat one by one natin siyang hinihimay, so we are deconstructing it, uh, or rather, it is being solved in a deconstructed manner, so ipapasok muna yung mga load, tatanggalin yung mga tinatawag natin na degrees of freedom, and then isa-isa natin ilalagay, so that is the concept of MDM, or moment distribution method, unlike sa slope deflection na sabay-sabay natin siyang masosolve, and what do we need to know, what are the terms that we need to remember, when it comes to concerning MDM, pero somewhat may encounter nyo rin siya, no, when you do slope deflection method, no. So first term that we need to remember are stiffnesses, no. So you are all aware naman na we are analyzing the beams, no, or let's say structures member by member, no, member by member, joint by joint, no. So each member, no, they have respective stiffnesses, no. So first type of stiffness, no, yung what we call the bending stiffness or the absolute stiffness, no, it is defined as the moment that must be applied at the end of the member that will cause a unit rotation at that end, no. So let's say you're given here, no, a beam, no. So we have here a hinge support on the left and a fixed support on the right, no. Next beam naman, hinge on the left and then another somewhat pwede natin sabihin na another hinge or just a roller support, no. Or no, so the hinge here, no, somewhat uh, uh, denotes na we are allowing yung rotation, no. So on this part of the beam, no, on the left side of the beam, no, and we are to determine, no, the moment na magkukos ng theta is equal to 1, no. So somewhat this is equal to 1 radians, no. So 1 radian, no, and that is your stiffness. Okay, no. So I think we can be able to solve that, no, using uh, what we've learned from our theory 1, no, o yung how to solve for the deflections, no. Either you try uh, direct integration, no, area moment, or conjugate beam, no. So from that, or virtual work also, no. So from that, no, we are able to get, no, the value of theta, no, and then we express Rm in terms of the theta that we solve, no. So kapag ang far end of the beam, no, is fixed, no, dahil on the other side, no, it restrains, pinipigilan niya yung rotation on its own side, no, o somewhat, no, the left support, no, mas mataas yung so somewhat, no, in order to maintain that unit rotation, no, it takes a higher value of moment, no, so to cause that rotation, rather than if it's a simple support, just a simple support, no, we allow the rotation on the right side, no, what mas maliit yung required na moment, no. So from that, if theta is equal to 1, no, yung K natin, yung stiffness natin is equal to 4EI over L. And then yung kapag simply supported naman, no, so K natin is equal to 3EI over L. And then if by given, no, our structural members uh, are all made of the same material, no, we can use yung tinatawag natin na relative bending stiffness, no. So we divide, no, all our absolute stiffnesses by 4E. So yung 4EI over L, divide mo ng 4E, no, K natin will be equal to I over L. No, this is for fixed far end of the beam. And then kapag simply supported naman, that is 3/4 I over L. Okay, no? So those are what we need to remember for stiffnesses. Next, yung tinatawag natin na carry over moment. No? So carry over moment, no? So Okay, let me plug that first. For carryover moment, no? Moment at the far end of the beam or frame member due to the applied moment on the near end. No, so dito, if you have a beam here, no, so alam natin pag nag-apply tayo ng moment here, no? So anong moment, no? Ilang moment ang magre-react, no, on the other support, on the other side of this span, no? So we are able to derive that also ang MBA natin, no? Kapag nag-apply tayo ng moment kaliwa, no? Ang magiging moment natin sa kanan will be equal to M over 2. Kapag fixed support yung far end. Pero kapag near end naman, no? So alam natin na simple support to, no? And wala tayong moment dito. Wala tayong moment sa kanan and rotation is just allowed. So therefore, carryover moment is equal to 0 kapag hinge ang far end. Okay? Next that we need to know, no? Term that we need to remember is what we call the distribution factors. No? So distribution factor, no, is a multiplier that distributes the moment applied at a joint among the members connected to it. No? So let's say, no? So kasi nga ang moment distribution method somewhat involves yung rotation, no? So mamaya ipapakita ko sa inyo yung how are we going, paano ba nagwo-work ito. Pero let us discuss first yung distribution factor, no? So distribution factor, no, ang ibig sabihin meron tayong moment, no, on the support, no, and somewhat meron siyang pinapasang moment at each span na involved siya. Let's say dito sa support at B, no? Meron kang moment at B dito, no? So somewhat merong moment na napupunta sa span BC, meron ding moment na napupunta sa span AB. So yung span sa kaliwa tsaka span sa kanan, no? So pero ang tanong, ilang percent, no, ng moment na yon ang mapupunta sa kanan, ilang percent din yung mapupunta sa kaliwa. No? So we assume na we let your MBC be equal to 3EI over LBC multiplied by theta. MBA is equal to 4EI over LBA theta. So we know na with respect to the support, no, there is a moment, no, moment AB, no, acting on it, and meron ding moment BC. And somewhat we know na ang moment na to, yung MAB at MBC natin, no, it's somewhat not in equilibrium. So para maging in equilibrium siya, no, maglalagay tayo ng pangbalanse na moment. Yun yung tinatawag natin na MB. Okay? So MB plus MBC plus MBA is equal to 0. MB is equal to negative of MBC plus MBA. And then we put yung MBC natin at saka MBA natin here. And then we just found out, no, na this is yung MB natin is equal to negative of KB plus KBC theta. And that is also equal to the summation of K sub B, theta. And then pag nilabas natin yung 4E, no, those are the absolute stiffnesses. Pag nilabas yung 4E, magiging relative stiffnesses na siya. And then M sub B is equal to negative 4E summation of KB theta, yung relative. Theta natin is equal to MB over 4E summation of KB. Isa-substitute natin tong theta na to, no, sa M sub BC tsaka sa M sub BA, no, we can obtain the following, no. And we just found out na ang distribution factor pala is equal to the relative stiffness, no, over the total stiffnesses. Okay? No, so you have to remember na summation of stiffnesses is always equal to, no, which denotes 100%. Okay? No? Also, at the same time, no, pwede nyo rin gamitin yung absolute stiffness as uh, means to compute the distribution factor. Okay? No, so let me discuss to you the concept, and mamaya I will show to you, no, how are we going to, how is it mathematically applicable, no? Yung paano ba, bakit ba ganito? Bakit natin gagawin to, no? And how are we going to explain it in somewhat mathematical form? Okay, so the first thing that we need to do, no? So we determine all the joints that can rotate freely, no? And then we assume everything to be clamped, no? So tanggalin lahat ng joints natin na nakakapag-rotate, no? So let's say you have here a continuous beam, no? So nakaka-rotate yung roller natin sa gitna, nakaka-rotate din yung roller sa dulo. So we clamp it, no? So we restrain all movement. No? So we assume na fixed tayo dito, fixed tayo sa span AB, fixed din sa span BC. So ano ang moment na nag-act dyan? No, that is your fixed end moment. No, so nakalock yung, so una ilalock muna natin, no? So we are going to lock all our supports, no? And then we are going to release, no, yung support natin, no? So i-release natin yung support natin dito sa gitna. So pag ni-release natin yung support, no, and then nakalagay na yung fixed end moment natin, we know na yung fixed end moment natin are just unbalanced. No? So hindi balance yung moment natin kahit pag tinanggal natin to, alam natin na hindi balance yung fixed end yung moment natin dahil do sa mga fixed end moment. So ngayon, we are going to allow rotation, no? And then we are going to balance yung we are going to determine the amount of moment na kailangan para mabalanse yung moment na nag-a-act doon sa support. Okay? So the unbalanced moment shall be balanced by removing the clamp and letting the joint rotate. Balanced moment will cause another moment at the other end of the span. No? So ngayon tapos na tayo ngayon with respect to joint muna, no? So with respect to joint, alam natin na may unbalanced moment, so ibabalance natin. Pero, no, at the same time, yung balance moment natin, no, pag in-apply na natin yung balance moment natin, somewhat it will cause, no, moment, no, on the other side of your span. No, so yung unbalanced moment natin dito sa gitna, somewhat magko-cause ng moment sa kaliwa and also magko-cause din ng moment sa kanan. Okay? So paulit-ulit lang 'yan, no? Hanggang all moments na meron tayo are balanced na. Okay? So somewhat it's easier for me to explain to you, no, by trying to visualize it on a through the use of the slope deflection method, no? So let's recall all our slope deflection equations, no? So MBA is equal to FE no, plus 2EI over LBA times 2 theta B plus theta A minus 3 psi. MBC, no, M sub AB, no, and M sub CB. So balikan nyo yung mga nasa slope deflection method nyo. And then alam natin lahat na all supports will remain at the same level even after applying the load. So psi is equal to 0. And then let's consider joint B first. No? So for joint B, ito yung mangyayari. No? So FEMBA plus 4EI over LBA times theta B plus 2EI over LBA times theta A. No? So FEMBA, no, plus 4EI over LBA, no. So yung theta B natin dito, nakuha ko yan dito, no. So yung theta natin, no. So yung theta B, no, it's just equal to the negative M over 4E summation of K. M sub B over 4E summation of KB plus 2EI over LBA times negative MA over 4E summation of KA. FEMBA, no? Minus na yan kasi negative tayo dito. I over LBA times summation of KB, M sub B, minus I times over LB, summation of KA, times M sub A over 2. MBA natin is equal to FEMBA, no? Minus KBA over summation of KB times M sub B minus KAB over summation of KA, no, times MA over 2. No, so we just found out, no, na ito ay yung distribution factor, no, for point BA. Iba pa yung sa AB natin, no. So BA meaning B go to A. And yung M sub B natin dito is yung balancing moment natin na sinasabi ko kanina, no, na okay? So first, yari, no? Yung FEMBA natin, no? So wala muna yung FEMBA. This is due to the assumption all supports, no? All degrees of freedom are restrained, no? So nung nirelease natin yung clamp sa support at B, no? So meron tayong unbalanced moment, no, na binalance natin. So ito 'yon. And ito yung moment na napunta sa BA. B going to A. And then meron din tayong carry over mula dun sa support at A. Okay? No? So, yun yung sinabi ko doon sa process, no? Una, tinanggal ay nilock muna natin. Tapos, no, nag-cause ng unbalanced moment, no, on the support. So ngayon iba-balance. No? So ito na 'yan. Yung distribute, binalance, and then syempre meron din reaction from the other point of the span. Sa MBC naman, same thing will happen, no? So ganun din, no? So sa MBC, no, may unbalanced moment, no? So binalance, and then may carry over from the other side. Okay? No? So next, if we decide if mag-refer na yung una nag-refer tayo doon sa gitnang support, no? So on the mid support, no? May uh, na may jurisdiction ng dalawang span. Pero what if doon tayo sa mga dulo? Okay? Una, support sa kaliwa, no? No rotation, walang rotation, pero merong moment. No? So FEMAB plus 2EI over LAB times 2 theta A plus theta B. O nga pala, no? Going back here. Okay? Mamaya before we no, 2 theta A plus theta B, no? So FEMAB, no, plus 2E over LAB times negative M sub B over 4E summation of K. That is FEMAB minus I over LAB summation of KB times MB over 2, no? So FEMAB minus KAB over summation of KB times M sub B over 2. No? So, meron tayong, inassume muna natin na they are restrained, no? And then, wala tayong theta, no? Walang rotation, no? Ibig sabihin, hanggang sa dulo, we didn't allow any rotation. So, therefore, we don't need, no? There is no means of balancing the moment. No? So, hindi natin binalance yung moment sa AB. No? So kasi walang rotation na magaganap, no, hanggang sa dulo. Pero at the same time, from support at B, meron tayong carry over na tinatawag. So with no balancing moment but with carry over from the other end. Okay? So dito, no? So So therefore, si moment at A, no, at joint B, walang ipapasang moment si A papunta kay B. So I think wala to. No? Okay? So walang ipapasa na moment si A papunta kay B. Pero si B, merong ipapasang moment papunta kay A, no? Sa M sub AB, no, merong yung moment galing kay B, merong mapupunta kay A. Okay? May reaction kay A. No? Samantalang si B naman, no, walang reaction galing kay A. If support is hinge, no moment pero merong rotation, no? So M sub CB is equal to 0 is equal to FEMCB plus 2EI over LCB times 2 theta C plus theta B, no? Substitute them all. Okay? And then we'll arrive here, no? So FEMCB minus KCB over summation of KC times M sub C minus KBC over summation of KB times MB over 2. Okay? And alam natin na hinge siya, so therefore wala tayong carry over from moment at B. Walang carry over from B, and we see to it na kapag nag-balance tayo, no? So, nung una, meron tayong unbalanced na fixed end moment sa CB, and then it was binalance lang natin siya, and kapag nag-balance tayo, no, it will just result to 0. Okay? No? So, let's try to solve some problem, no? Para medyo mas maintindihan nyo rin yung concept. Okay? No? I will just illustrate that to you, no? So again, balik tayo, no? So dito sa joint B natin, sa joint B, no? Merong FEM or fixed end moment, no? So pag ni-restrain yung mga degrees of freedom, no? So pag binalance, no, when we allow the rotation, and then meron ding carry over from the other support. Okay? Yun yung kapag kami internal support in which allowed yung rotation. Okay? No? So kapag fixed support, no? Pag fixed support, we don't have to balance kasi it will just remain fixed, no, na walang rotation. Pero at the same time, no, there is a carry over from the other support. Kapag hinge naman, wala tayong carry over from the other support dahil nga simple support siya, no? And the same time, no, ang balancing moment niya will just be the same as yung fixed end moment. Okay? No? And paulit-ulit lang siya, no? That is moment distribution method is an iterative method nga, no? So let's try to solve some problem. So let's solve this problem, no? So you're given, no, O nga pala, no, before we try to solve the problem, no, so we have here the flow of how are we going to do uh, the moment distribution method. No, so we have first the fix and moment dahil nga una we restrain all the movement, all the degrees of freedom, and then we balance, no, and distribute, no, yung we balance the moment by allowing the rotation, no, and then distribute it per span, and then we carry over to the other span, to the other side of the span, no, and then rinse and repeat, no, until everything is balanced, no. So solving this problem, no, we have a continuous beam, no, with fixed supports on both ends, no, fixed support on A, fixed support on C, and then an internal support on B, no. So we determine, no, the moment, no, we determine, no, uh, we determine the moment, no, that acts on each point, no, sa point A, sa point B, sa point C. Okay, no? So of course, what do we need to do first, no, are determine all the distribution factors, no? Distribution factor for BA, no? So per span ang ano natin, no? So per point, per span tapos per point, no? So let's say we have a span AB, no? So meron tayong moment AB means A going to B, B going to A, B going to C, BC, C going to B. Okay? No, so let's determine, no, the distribution factors of the support in which rotation is allowed. No? So BA at saka BC. So DF ng BA natin, no, is equal to I over 5 over I over 5 plus I over 6. That is equal to 6 over 11, which is also equal to 0.545. I over 6 over I over 5 plus I over 6. That is equal to 5 over 11 over 0.545. 6 over 11, 5 over 11, we write it. We write all our solved distribution factors. 5 over 11 sa BC, no? So 6 over 11 sa BA. And then next, no, we clamp all our support, no? So clamp na yung A natin at saka C. So wala nga kailangan nating i-clamp, no? So we allow restrict movement sa joint B. So kapag ni-restrict natin yung movement sa joint B, no, we all know what that means, no? Meron tayong tinatawag na fixed end moment per span. Okay, fixed end moment dito AB tsaka BA. So BC, CB. So all our fixed end moment can be solved using yung formula na, no, just using we can be able to solve for fixed end moment using the formula that I provided, no, or other, no, you can try solving using integration, or gusto nyo use yung mga previous method na natutunan natin. FEMAB is equal to P, no? So concentrated load yung sa AB natin, span AB. So FEMAB is equal to negative 90, no, times A is equal to 2, 3 squared over 5 squared. A, B squared over L squared. No, we have negative 64.8. No, so negative 64.8, that means siya ay counterclockwise. No, so fixed end moment, ang sign convention natin for fixed end moment, no, yun yung equilibrium sign convention, no. So for BA naman, no, so FEMBA 90 times 3 times squared over 5 squared. Okay, that is equal to 43.2 kilonewton meter, no. So we write negative 64.8, 43.2. Okay, next, FEMBC is also the same as CB na pinagkaiba lang sign convention. WL squared over 12. 50 times 6 squared over L, which is equal to negative 150 kilonewton meter BC. CB is equal to 150. No? So we write them down here. 150, 50. Okay? No? So meron na tayong mga fix and moment. No? So sa fix, kapag fix support sa A at saka sa C, ang sabi, walang balance. No? So hindi natin siya ibabalance. No? So meaning, no, yung negative 64.8 sa point AB tsaka sa point CB na 150, no, will just stay there. Okay? So that is our balancing moment at AB at saka CB are both 0. Okay? Pero dito, no, sa BA at saka BC, no? So sa BA, meron tayong dahil dito meron tayong clockwise, we have a counterclockwise na 43.2. And then dahil dito meron tayong counterclockwise here, meron tayong clockwise na 150. So ang balance moment niya is technically this. Okay? No? This is our unbalanced moment. Pero of course, in order for it to be on equilibrium, no, what we need to do is, ang balancing moment niya will be this one. Okay? Okay? So, yan yung balancing moment niya, no? Which is equal to, okay? Yung resultant ng 43.2 natin tsaka ng 150. No? Which happens to be negative 150 plus 43.2. Okay, that is negative 106.8. Okay? So, clockwise siya, no? So, counterclockwise siya, no? So, ang pag nilipat no? So, again, no? So, ito sa with respect to the joint, no? Clockwise ang resulting moment natin. Pero, of course, ang magbabalance is counterclockwise moment, no? Na kapag dinistribute na natin sa kabila, no? Yun yung kabaliktaran, no? So meron tayong 150 minus 43.2. Meron tayong 106.8. Pag distribute natin yung 106.8 kilonewton meter sa BA, no? I-multiply lang natin siya ng 6 over 11 times 6 over 11, no? That will be equal to 58.255, no? Okay, so meron na tayong balancing moment sa BA. Okay? So pagka magdi-distribute naman pagka naman nilagay natin yung balancing moment sa kanan sa BC, just multiply this by 5 over 11. 48.545. Okay? No, so ang ginawa ko, may resulting moment itong dalawa na to, no? Na may resulting moment pero unbalanced sila, so ang magbabalance yung kaligtaran nitong sign convention, no? So kaya positive to. Okay? And then yung resultant nitong dalawang moment na to, yung dalawang fixed end moment natin, no? I-multiply natin sa distribution factors. Yun yung amount of moment na mapupunta with their respective points. Sa BA, ang mapupunta sa kanya, no, is 58.255 kilonewton meter, no? Ang mapupunta sa BC, 48.545. No? Galing 'yon dito sa resultant ng 150 at saka 43.2. Okay? So pagka-allow natin ng movement sa joint B, no? No? So yung of course, merong yung moment na yung balancing moment natin, no, will also cause moment on the other side, no? So yung 58.255 magko-cause siya na moment at point A. So nag-cause siya ng moment na kalahati, no, which is equal to 29.128. No? So yun yung carry over moment natin. Yung 48.545, no, nag-cause siya ng carry over moment na 24.273 sa point C. Okay? No? So 0 naman tayo dito, no? Sa AB, wala siyang ipapasang moment sa BA, no? So yung dahil 0 naman yung balancing moment natin sa AB, no, wala siyang nalipat na moment sa BA. Yung C natin, balancing moment 0, no? Wala rin siyang nilipat na moment sa B. Okay? So 0 na 'yan, no? Kapag nag-balance tayo, pag binalance natin, no? So therefore, dahil yung A natin, meron pa tayong natirang carry over na moment, no? So kapag binalance natin, dahil alam nating fixed support to, we don't have to balance it, therefore 0. Sa C, dahil fixed support din, 0, no? So dito 0 na yung resulting moment natin, therefore 0, no? So tapos na tayo diyan, no? And our process ends here, no? So ngayon, ang gagawin natin, we add all the moments that we have, negative 64.8 plus 29.128, we have a resulting moment of 35.672, no? And we have a 101.455, negative 101.455, and then 174.73. These are the final moments. No? So expected na yung BA natin at saka BC are the same. Ang pinagkaiba lang, the sign convention, meaning, no, yun yung direction niya. Okay? Here are the fixed end moment, no? End moments rather, no? So ito na yung mga final answer natin for the moment. Pero for the reaction, no, of course, we solve it this way, no? So pag tanggalin muna yung mga end moment, no? I-retain yung load, no? So meron tayo assume na simply supported siya. Okay, we have here 54 and 36 dahil sa 90 kilonewton na concentrated load, dahil sa 50 kilon per meter na distributed load, no? Hati siya 150, 150. May 150 na upward tayo dito, 150 na downward sa support. 36 na upward, 36 na downward sa support, no? Total of 186 kilonewton. Okay? Dahil sa pag tanggalin yung mga original load, ang ipalit yung mga moment natin, no? So we have 35.672 here na counterclockwise, negative. We have here 101.55 na clockwise, counter, then clockwise ulit. Okay? So, kunin ng resultant nila, no? So, 35, no? So, alam natin na mas mataas ito, no? Mas mataas ang 101.55. So, therefore, ang resulting moment natin is clockwise. So, ang kokontra sa kanya ay counterclockwise. So, therefore, pag nag-moment ka on this point, no, alam natin na counterclockwise yung dapat yung maging moment. So, therefore, pababa yung reaction dito. And then, pataas to. Dahil yan lang naman para maging equilibrium ang force natin. Okay? Next, dito, 174.273, 101.455. Alam natin na clockwise ulit yung resulta. Dapat counterclockwise ang kokontra. And ito yung lumabas dyan. Okay? We have here in upward load. So, downward dito. Downward, so upward yun. So, meron tayo resulting na 1.021. No? 12.136, 13.157. No? So, 54 minus 13.157 is equal to 40.843. 186 plus 1.021, 187.021. No? 150 plus 12.136, 162.136. And we have the respective moments here. Though this is now our reactions. Okay? Okay, so let's now refer to this problem. No? So you're given another set of continuous beam, no? Two-span continuous beam, no? A, B, C, with fixed support at A and a roller at C. No? So somewhat different from our previous problem. no? So all have the same length, no? All span have the same length, 10 meters, and acted on by a concentrated load 80 kilonewton on the middle of span AB, and 40 kilonewton concentrated load at the middle of span BC, and we have 1.5 I and I, no, sa on span AB and span BC respectively, no? So E is assumed to be constant, no? So we determine all the end moments, no? So tatandaan nyo, kanina may mga condition tayo for simply supported beam. For simple supports, no? So i-apply natin lahat 'yon dito. Okay? No, so first we need to determine the distribution factor for BA and then BC, no? So kasi ito lang yung may dalawang span, no? Ito lang yung may sakop na may dalawang span. Tapos the same time, no, it's the only support that is allowed to rotate. Syempre maliban din dito, no, C is also allowed to rotate pero somewhat B is different, no? So we determine the distribution factor, no? So relative stiffness ng AB, no? So or BA is equal to 1.5 I over the length, no? So 1.5 I over 10 over 1.5 I, no? So 1.5 I over 10 plus 3/4, no? So nga pala, dahil roller yung nasa C natin, no? Roller ang support sa kabilang end, no? So mo-multiply natin ng 3/4 yung relative stiffness, no? So nakita nyo dito sa notes for MDM, ayun, no? So this one, okay? Hinge far end. Okay. So mo-multiply natin siya ng 3/4 I over L, yung relative stiffness. So lalabas 2/3. Okay, DFBC is equal to 3/4 I over L over 1.5 I over L plus 3/4 I over L is equal to 1/3. Next, put all the distribution factor. 2/3, 1/3. So mamaya, dahil yung mga principle na natutunan natin regarding fixed support and roller, no, meron din tayong distribution factor para dyan. No? Pero yung principle muna natin when for fixed support tsaka roller, yun muna ang i-apply natin. Okay? No? So determine all the fixed end moment, no? Fixed end moment AB and BA are just the same. No, that is just equal to 80 times 5 times 5 squared over 10 squared, negative 100 counterclockwise. No? So negative 100, positive 100. Okay? Sa BC at saka sa CB naman, just the same, 40 times 5 times 5 squared over 10 squared. No? So negative 50, positive 50. So we have now your fixed end moment. So next thing that we need to do, we balance it. Sa fixed support at A, we don't need to balance kasi wala naman tayong tatanggalin na fixed support dito. Wala naman tayong i-allow na rotation. No? So therefore, balancing moment at AB is equal to 0. Dito, tatanggalin natin yung moment. Tatanggalin natin yung moment. So the balancing moment shall just be equal to the fixed end moment. So negative 50. Okay? No? So ngayon, ang ibabalance naman natin will be yung BA at saka BC. So sa BA at saka BC, no? So alam natin na dito meron tayong clockwise dito. Meron tayong counterclockwise sa BC. Pero with respect to the support, so meron tayong counterclockwise, meron tayong clockwise. Ito, meron tayong 100 na counterclockwise, merong 50 na clockwise. So meron tayong resulting moment na counterclockwise, and then para mabalance yun, kailangan natin ng clockwise. And para sa clockwise, i-distribute natin siya sa BA at saka sa BC, no? On the opposite direction. Okay? So, meron tayong 50 kilonewton positive. So, para ma-balance, kailangan natin ng 50 kilonewton na negative, no? And i-distribute sa BA, no? Multiply natin ng 2/3 yung 50 kilonewton, negative 33.33. Yung BC multiplied by 1/3, no? Negative 16.67. Okay? Next, yung balancing moment natin dito sa BA, no, will cause a moment at AB, no? Meron tayong carry over moment sa from BA papuntang AB, no? That is equal to the half of 33.33 negative 16.67. Pero dito sa BC naman, simple support yung nasa C natin. So therefore, wala na tayong carry over papunta sa C. So 0 na tayo dito. Diretso 0 na tayo sa CB. Okay? Next, meron pa tayong negative 50 galing sa CB. No, i-carry over natin siya papunta sa CB, sa BC, no? Okay? And then next, yung negative 25 na to, ibabas natin siya. Ito na yung lumabas, positive 16.67 and then 8.33. Again, itong 8.33, wala nang i-carry over papunta sa C. So 0 na yan, diretso 0. And then ito, may i-carry over pa papunta sa A, 8.33. No? Pag binalance, that is 0 already, 0, 0, 0, 0. So ibig sabihin, tapos na tayong mag-compute, no? Get the sum, no? 0, negative 83.34, positive 83.34, negative 108.34. Just get the sum, no? Mula taas hanggang baba. Taas hanggang baba, taas hanggang baba. Okay? No? So those are our end moments. No? So AB, negative 108.34 kilonewton meter. 83.34 kilonewton meter, negative 83.34 kilonewton meter, 0. Okay? No? So, here is how we solve for the reaction. No? So, the usual lang naman. No? Tanggalin yung mga end moments. No? So, meron tayong simple support lang, no? With the original load. No? And then, tanggalin yung original load, ilagay yung mga end moment. No? This is how will it resolve, no? Kindly check na lang, no? So kindly check and then try to practice. So let's move on to the next problem. So next problem, no? Just similar to the problem number 2, but we have an overhang CD here, no? Acted upon by a load of 30 kilonewton concentrated load, no? So how are we going to do it, no? So note that treat the overhang as a cantilever beam. So yung CD natin parang cantilever siya, no? And then the rest of the beam as an indeterminate beam. But the moment from the overhang should be included in the moment acting at the support at C or the nearest support. So paano natin gagawin 'yon, no? So ihiwalay natin yung CD, no? Parang cantilever siya here. Ito yung CD nyo, no? Hiniwalay natin siya. So parang cantilever siya na fixed support lang. And then we are going to analyze beam A, B, C. Pero don't forget, no? Nang ina-analyze natin to sa cantilever beam, meron tayong moment here. So therefore, meron din siyang kasamang moment na mag-a-act, no? Doon sa original na beam, doon sa beam na gagamitan natin ng moment distribution method. Okay? So therefore, no? So paano ko gagawin 'yon, no? Paano natin gagawin, no? So mamaya, no? So ang explanation diyan, no? Yung 120 kilonewton dito, isasama natin siya as analysis pag nag-analyze tayo dito, no? na yung counterclockwise na 120 galing sa pag-analyze natin as cantilever, papasok natin dito na on the opposite direction. Okay? So let's determine the distribution factor first. df I over 6, no? Over I over 6 plus 3/4, no? 3/4 kasi, no? At BC is simply supported. 3/4 ng I over 9 is equal to 2/3. Then df ng BC naman, 3/4 times 1 I over 9, no? Over I over 6 plus 3/4 ng I over 9 is equal to 1/3. Okay? So we put now our distribution factors. Okay? 2/3, 1/3. Okay? No? So let's solve for the fixed end moment. Meron tayong distribution factors. FEM naman. Or fixed end moment. FEM, AB, and BA. Wala tayong loads dyan. So both are 0. 0, 0. No, we have naman BC at saka CB. No, that is just WL squared over 12. No, that is equal to negative 67.5 and positive 67.5. Okay? No, sa 120 naman, isang beses lang natin siyang isasali dito sa as FEM, negative 120. Okay? Next, we balance it. No? So balance. Para ma-explain ko din, i-explain ko din paano natin isasama yung 120 na galing sa overhang, no? So, meron tayong, di ba? On this support at C, meron tayong 67.5 na clockwise with respect to the span. Pero with respect to the support, that is negative 67.5 or counterclockwise na 67.5. Meron tayong 120 na counterclockwise, meron tayong 120 na clockwise. So kapag pinagsama natin yung 120 kilonewton, 67.5, meron tayong resultant na clockwise. Pero para ma-balance natin yan, kailangan natin ng counterclockwise na moment. And then, pag nilipat natin sa kabila, siya ay pag nilipat natin yung balancing moment, with respect to the spans, with respect to span CB, pag nilipat natin, kabaligtaran siya. And we're just going to multiply, we're just going to just put it here, So lalagay lang natin siya ng buo, Pero alam natin, alam natin na yung resultant, so 120, meron tayong resultant na 52.5, 120, 67.5. Pero para ma-balance natin yan, kailangan natin ng counterclockwise na 52.5 with respect to the support. Pero pag with respect to the span na, kukunin niya ng buo yung moment mo. So that is equal to clockwise na 52.5. So ito na yun. Positive 52.5. Sa AB at saka BC naman, wala tayo. So meron tayong negative 67.5 ni unbalanced moment. Para ma-balance, positive, multiplied by 2/3 tsaka 1/3. So ito na yun. Yan. And then yung 45 kilonewton na to, may carry over sa AB, kalahati, 22.5. Yung 52.5 papunta galing sa CB papunta sa BC, 26.5. 22.5, dahil simply support to, walang mapupuntang moment sa CB, zero na yan. Okay? So fixed support. Okay, fixed support 0, walang balance. Okay, pag binalance yung 26.5, 17.5 tsaka 8.75. Okay? So 0 na yung carry over natin sa CB. So 0 din yung pang-balance. Okay? So may carry over to sa kabila, 8.75 na negative. So negative 8.75. Or rather pa. So okay? That is 8.75, no? So, negative 8.75. And then, pag binalance natin siya ulit, that is equal to 0. Wala na. Wala tayong kailangang i-balance sa A, no? So, wala na ring i-balance sa BA at saka sa BC. Wala na rin i-balance sa CB. So, that will end here and get the total. 120, negative 120, negative 27.5, positive 27.5. No? Tapos, we have 22.5, 8.75. Okay, those are the total. Okay? And also, wait lang. So let me correct myself on this part. No, this is negative 17.5. May kinary over siya na negative 8.75. So dapat this is not 31.25, I think. No? So 22.5 minus 8.75. That would be equal to 13.75. Okay? No? So that is how you solve for the member and moment using moment distribution method. No? So iba-iba ay pareho lang yung process pero medyo nagtutweak lang tayo ng konti sa approach, no, depending on what type of support do we have, no? So yung principle lang niyan, no, we restrain all the degrees of freedom first and then we are releasing it, no, gradually, no. Okay. Okay, so for additional information, no, you can try also in order to uh, somewhat ease the confusion, no, regarding fixed supports and simple supports, no. For fixed supports, no, fixed ends or fixed supports, you can try to use distribution factor of 0, no. So bakit 0, no? Kasi if you can remember, no, yung what I taught you nung sa 3 moment equations, no, kapag pagka fixed support, no, usually nag-a-add tayo ng additional na imaginary span, 'di ba, na ang length niya ay 0. Okay, no? So kapag pag kinuha natin yung summation ng stiffness niya, no, we know na it will be infinite, no, kasi ang stiffness niya ay typically either 4EI over L, no, or just I over L, no. Ang L natin for the imaginary span is equal to 0, no, so infinite na yon, no. And of course, no, any number divided by infinity, no, it will be equal to 0, no. So kapag simple support naman, no, whether may overhang yan or wala, may moment or wala, no. So pag simple span, no, if we do summation of its stiffnesses, no, since isang span lang ang meron tayo dun, wala na tayong imaginary span, no, the stiffness, no, divide by the sum of stiffness, dahil isa lang ang stiffness natin doon, no, you are just to divide it on with the same number, no. So our distribution factor there will be equal to 1. Okay, so ang tinutukoy kong distribution factor, ito yung kapag ito yung depende kung anong klaseng support yung nandun sa banda, nasa edge, no, or nasa dulo, no. Hiwalay pa yung nasa gitna. Okay, so I think that ends our video, no? So uh, if time will permit, no, I will try to give you a little. Uh, we will try to solve uh, problems on frames with outside sway and frames with side sway for this method, no, the moment distribution method, no. So if you have any questions, no, don't hesitate to ask, no, leave your comment, no, leave a message, no, to me, no, to the Blackboard, through my email, through my social media, no, or and also if you want to be updated of the latest videos, no, you please like and subscribe, no, to this channel. Okay, thank you, no, and see you on the next video.